Okay, so here we are in the second section of our review of using and understanding simple linear regression using RStudio as both a platform for interpreting statistical analyses and output, and also as a platform for understanding statistical analyses and output. And I would encourage you to actually view R not as something passive, but as a tool for learning. Because as one programmer had once taught me, he said, this was a computer programmer, he once taught me that if you want to learn how to swim, for example, you want to go swim laps in a swimming pool. You can read many, many books about swimming, but you won't necessarily be a competent swimmer by reading only books about swimming. I would make the same argument about statistical analyses. Namely, learning and understanding concepts are aided and abetted by understanding the data and getting a feel for getting your hands dirty, as a friend of mine, as a colleague of mine would say, in the sense that you are playing around with the data and think of it as a method of exploring and understanding the data. And if you can think of these statistical tools, such as simple linear regression, as one tool in your toolkit for understanding the data at hand, I would encourage you to view statistical analysis in that way. That is, that's more of an iterative process. It's more almost like a Zen-like process, if you want to use speak more metaphorically. There is sort of a Zen-like process where you do interact with the data. It's not a method of hacking the data by looking and understanding the context of your analyses. It's more of an interactive process. And I think R is both good for interpreting and data outputs in real life contexts, which is quite often your biggest challenge will be actually understanding and interpreting output for many people who frankly do not have time or do not have the interest in the nitty-gritty details. But there's also this element of teaching and using R as a platform. So I just want to emphasize that. And to that extent, one of the students attending this section had asked about understanding variance of the outcome and how do we decompose the variance of the outcome. And I hope this will explain that issue when we talk about this idea of prediction. That is, what is the value of y for a particular value of x? And I focused on prediction because I think it's the main distinction, the main conceptual distinction between simple linear regression and its close cousin, correlation. Before we continue with the rest of the code and this idea of prediction, which involves writing out the equation for the regression line, I want to review what we had talked about in the previous section, which is loading your data into R. That's the first on line 60. And this is not in the code that I provide for homework. This is actually typed in. And you can see this in the previous R video. But the first concept, loading your data into R, I took quite a bit of time, and you'll see me taking more and more time, or rather less and less time, but probably more time when we use R for understanding and really learning about statistics, because this is a major issue. I consider it an issue of what we call data hygiene, in the sense that you want to have R as your sandbox. So you really want to know your data. And so I talk about loading data, but really I should probably bracket this and say this is more about an issue of data hygiene, which is the broader concept of sort of the spelling hygiene. My apologies. Did I spell that? I don't know. I think R will do many things. It will not do a spell check on you. So data management, you could even say. That's easier to spell. But the point is that R is not just a computer programming language, and Mosaic and RStudio are not just a sort of a more user accessible platform. It is also a tool that is aided and abetted by keeping your work environment clean and understanding what it is that you put into your data, your environments, or what I often call your your sandbox, but here we can call this your global environment. And we talked quite a bit about that. Then I talked about interpreting and understanding linear regression vis-a-vis correlation. That is, what is the difference between this? And I emphasize 2 points of really understanding our code, which is through the console panel. And I'm going to start annotating so you can actually see where I'm putting my mouse, because I realize that you may not see this. I'm going to do a little highlight here. This console pane right here in the lower left-hand corner. And then you see in the right-hand corner, you'll see the plots pane, which these are the 2 axes, the 2 points in which your code, you interface with the data, and you create more condensed and coefficients and outputs. And that's what is tested in the midterm and the final exam, but it's also what it is you're going to encounter when you do data analyses or data interpretation of analyses. And the main point in the second concept is that the main difference between, the main difference between simple linear regression and correlation is that simple linear regression is focused on this idea of prediction. This is why we're talking about an entire section focusing on prediction. Because we're talking about what is the value, the mean or expected value of a y variable given a particular value of x. That's really the main goal of simple linear regression, I would argue. Although there are many different other different kinds of ways of interpreting the association between one numeric variable with another numeric variable. But really that's the advantage, and that's really the flexibility of simple linear regression. And the reason I'm speaking and focusing so much on simple linear regression, if you notice I'm kind of keeping the sections a little more tightly wound and around these concepts, is because simple linear regression is something that does not go away. I call it the workhorse of statistics. Believe it or not, after 10 plus years of doing statistics and doing statistical consulting, I can tell you that I am doing it, I'm focused around, I still do linear regression today. I don't do as much correlation, but simple linear regression is the basic, it is the foundation of all statistical analyses. And in fact, even though, you could say there are a lot of questions about data science in terms of like, what is a data scientist doing in this year and at this time point, I would say simple linear regression is the foundation of so much of statistics and so much of data science today. Really, you could talk about prediction algorithms all you want. Say if you use a social media site and it predicts your personal interests, that could actually be interpreted. A lot of these predictive algorithms that we talk about, a lot of these predictive algorithms can be interpreted within the linear regression framework, believe it or not. We could think of, say, I'm using, say, a video streaming site such as YouTube to watch documentaries, to learn a language, let's say to learn French. And then I see in the prediction algorithm that I see more videos in French. Well, why would that be the case? Well, because a prediction algorithm was used based on some vector of x values, my previous viewing history, and then the algorithm predicts the outcome y. So the exciting thing about simple linear regression is that it doesn't leave you, ever, really. We are all bound by simple linear regression. So when we talk about algorithms of predictive algorithms or predictive analytics, I'm throwing out some jargon today. We could actually think about much of this in terms of, if not all of this, to be honest, I'll be bold enough to say all of this. It's okay to talk about prediction within that framework, within the linear regression framework, because we could say maybe there's a weighted mean, a weighted expected value of my previous viewing history. And by that I mean we just do some sort of average of what it is the algorithm would expect me to view in the future based on my viewing time for each video. So it would be like the number of videos weighted, that is plotted against some linear combination of viewing time plus or times the number of videos I've seen. Of course, it is more complex than that, but the foundation is still based quite often in linear regression. And we'll, in future classes, even at the end of this class, we'll dive a little bit into multiple regression, which is an extension of simple linear regression. And then another extension is called generalized linear regression, which simply says we don't have to assume that this y variable is numeric or continuous. We can actually predict a categorical variable, such as yes or no, given a vector of x's, or value of x, or multiple x's. So the point is, simple linear regression, it's going to be there. I know. And that's why this is a really exciting part of this class, I think, is that, you know, given a few weeks into statistics, you're already doing what seasoned data scientists are grappling with. So I think that's probably the most exciting part of this class, that you already are going to be equipped with the tools to use R, which is used by Google and many other major companies, to understand and interpret using essentially the tools that we still use. And here is where I talk about the understanding the data in the context of the analysis. Because unlike correlation, simple linear regression and all of its variants require some element of context. Now, some people might say, well, Dr. Fossey, when we talk about regression or algorithms, we talk about machine learning, and the machine is doing a lot of the learning. Well, that's true, but the inputs require some sort of interpretation. And a machine learning a particular task only makes sense within a human context. So machines are now, say, predicting viewer or usage on, say, a social media site. Well, here we're talking about, still talking about the context and of the data and the analysis. And this is really, I think, the interface between humans and machines. Yeah, the regression will spit out as much code as you want, as many results as you want, but it only makes sense if a human is there to communicate it, really. And that's going to be difficult to get rid of, and also probably more and more important when we have more data than we can actually understand and analyze. And then I talked about the details of the simple linear regression model, this idea of the intercept, the slope, and then finally the R squared. And I'm going to review the intercept and the slope and the R squared when we talk about prediction. But the main point is the intercept, the slope, and the R squared are different elements, different pieces of understanding how one numeric variable, or x, is associated or not associated with a numeric variable y. And I should say linearly associated. And using this idea of prediction, we can call x a predictor variable, and then y the expected value, or the outcome variable. We can understand the simple linear regression model as an interpretive framework as much as it is a simple mathematical model. So let's go to the simple mathematical model. For this homework assignment, we do ask you to do some variant of this prompt, which is to write out the equation for simple linear regression, predicting murder rate using the input variable rural. Pardon, I'm just drinking some water. And this builds on our previous analyses. So let me clear the console. I'm doing command, hold on, this is muscle memory. Doing control L on my Macintosh interface. And what I did is I just actually erased my workspace, my console, but I actually didn't erase the history. You can see the history right here. And you can see that I ran all of the code, but I wanted to run the code up until this point. And so here we have something called the model, but we're going to remove the model. And I'm just going to type this out because I don't want to save this issue. I want to remove that model bit, but I'm going to keep the data frame. And I want to clear this history just because I like to have a clean console. It's my personal preference. I want to run this code given that we've uploaded the data set, just to review the output. And I spoke quite a bit actually about a scatter plot, but also about viewing and exploring the data. So I'm just going to click the run button here to run the highlighted code. And it's all automatic once you have the code put in. And what you can see here is that I produced a scatter plot between one variable, an x variable, that you should be able to see. Let me change the screen size. Rurality, which is the percentage rurality in a country, and then its murder rate, which is per 100,000 people. So as you can see, you can already see the major distinction in a scatter plot of two variables is that the correlation coefficient that we spoke about before gives us a nice standardized summary that permits us to compare across contexts the magnitude of the association between two variables. But a correlation really fails us to provide us of information regarding the context. And I spoke about these first the intercept and then the slope in the regression framework, and then this idea of the R squared, which is the proportion of variance explained in the outcome as a function of the input variable x or predictor variable x. What this means is that the variation in our outcome y, which varies from 0.55 to about 59, to exactly 59, this is the variation in that outcome. It ranges from, it has quite a bit of variation. And this is why it uses the fabstats function to show to you that the standard deviation is about equal to the mean, which is 22.5 in this data set. So the idea is that given that we have variation in the outcome y, can we use our predictor variable to explain it? And here we have this percentage rurality. So it has some of the limitations of correlation analyses, especially in a observational data set, which is that a linear association is assumed, first of all. But most importantly, when we talk about interpreting the association between two variables, even in the simple linear regression framework, we cannot talk about causality. But we can talk about prediction. We can say, given our value of rurality, what does this tell us about our outcome? And we talk about the proportion of variance explained within the simple linear regression framework because that is a summary statistic that explains overall how well does our model predict our outcome. And what the R squared does, I'm actually starting kind of backwards because we talk about R squared we talked about R squared last. The R squared is the proportion of variance explained in our outcome y as a function of our variation in our input variable or predictor variable x. That's the most intuitive interpretation. What it means is that an R squared of 1 would mean that 100% of the variation in our murder rate could be explained by rurality. And that would look very much like, actually exactly like a correlation of 1, positive 1, which would mean a perfect one-to-one correspondence between rurality and murder rates. So if we could imagine hypothetically a correlation in which there's I even misspoke, an association that is perfectly linearly dependent or predictive, it would mean that if we knew rurality, let me be clear. In the case in which R squared is 1, 100% of the variation in our outcome is predicted by our predictor variable. On top of that, we would have a one-to-one correspondence between our predictor variable x and our outcome y. So if we knew what, say, rurality was at 30, we could predict with 100% accuracy, all other assumptions aside, the outcome. And I think this concept of prediction is going to be clear when we superimpose a linear fit line on top of this scatter plot, which is something we didn't do. So actually I'm going to start there. But the other two bits of information, just to review, is this idea of the intercept and the slope, or intercept coefficient and the slope coefficient. And let's unpack that. So the intercept here is the value of y when x equals 0. So whatever this value is, it is in the units of the y variable here. So it is 13.33, which is about within range of the magnitude that we'd expect given the y variable. It's counted in tens on the y-axis. The computer software does that for us automatically because this is the range that we have in our data set for the y variable. So the absolute value of this intercept makes sense. But notice it's negative in our data set. Well, it gives us units of our y variable, but it often does not make sense to understand the intercept unless we can actually have a meaningful understanding of our x variable at 0, and we are interpreting our y outcome within the plausible range of values for y. And you can see that this is an important issue where context is raised, because an intercept of negative 13.33 could make sense hypothetically, but we don't live in a hypothetical world, we live in this world. And in this world, our murder rate cannot go below 0 per 100,000. So our intercept, which is our predicted value for y given x equals 0, does not make sense because it is negative at negative 13. So the 0, the origin of this xy graph, or the 0 point, doesn't really make sense. And conversely, you could even say maybe the extreme points at other data values might not make sense. But there are some other assumptions in the linear regression framework or model, such as most notably the linearity assumption, that may not make sense either. But that's important for the intercept. So to repeat, the intercept is the predicted value of y when x equals 0. And it is in units of the y variable. So here context matters. The slope in the R environment is going to be produced like this, with rurality being the name of the variable. So we know that the name of the variable is rural, and we know this because we looked at the data, right? We kind of looked at quite a few variables. But we knew rurality was there, and I can click on the data set here, and you can see rural right here. It's a numeric variable. And this right here doesn't say the word slope, if you notice. So the intercept is a coefficient that is created in the linear model, but same with the rurality coefficient. And what does this mean? Well, this is the slope is the value, the value, let me put it this way. The slope is also in units of y. Notice we're talking about prediction, but it tells us, it would predict for us how much we would expect y to increase with a 1 unit increase in our x variable. So it's basically the slope of our line, and this is the intercept. But you won't see the slope of the line actually modeled here in the coefficients outputs. And that's quite common. There's quite often numbers presented that you may not really understand immediately, but try not to get too intimidated by it. Just remember that, at least in the R framework, this is what the output will look like. We didn't really talk about this concept of coefficients in general, but I think it's important to focus on because we understood the other parts here. We talked about R squared as the proportion of variance explained in our Y outcome. So it's kind of tells us how much of predictive accuracy our X variable has. And our intercept and rural coefficients are labeled thusly, but they also tell us other aspects of the prediction model. Namely, what is the slope and what is the intercept? Now, the idea of coefficients, if we break down the word coefficient, it's simply a summary statistic. We talk about the R correlation coefficient, if you notice this, we'll talk about coefficients quite often in statistics when we talk about any kind of summary statistic in a linear modeling or modeling framework. Coefficient here refers to some summary statistic that represents or models the data at hand. That's really it. Coefficients is just a fancy term for summaries, numeric summaries of the data at hand. You could say that. But coefficient is something that we, don't be intimidated by that, but it's important to realize that coefficients can mean a wide range of things and requires an understanding of the model at hand. So if we talk about the correlation coefficient, we might have a Pearson correlation coefficient. We might have some other coefficient of variance. In class, we talk about a coefficient of R squared is a correlation as a coefficient, but also these other concepts are coefficients as well. It's simply just a fancy word for numeric summaries of a particular model. But think of the correlation coefficient as a different model that isn't predictive, but is more generalized. It's a more abstract description, but it doesn't provide the predictive power, because if you notice, these coefficients are in the units of x, in units of y, because we're interested in what's going on with y. That's our outcome variable that we want to predict. And this is where the interface between statistics and machine learning is most evident, because we can put in any combination of predictor variables, and sometimes the predictor variables might not even be that important. They might not be causally related. In fact, it may not be obvious why rurality would be associated or predictive of murder rate, but it is. And that in and of itself is informative. That's information, because it tells us that given what we know about rurality, we might be able to say something about the murder rate. Now, like anything in statistics, there's some chance involved. So it's not a 100% correlation or prediction. Okay, so notice I'm talking quite a bit about prediction, but I've also, at the same time, reviewed the concepts that we've spoken about. Are there any questions at this point? Otherwise, I'm going to be sure that I'm going to continue with the concerns or questions that were raised earlier. Okay, well, if there are any questions, please let me know. What I want to do is I want to get us out to, you'll notice I added some stuff here about the equation, but I want to get us away from the math a little bit and actually go back to this association between rurality and murder rate. And here we have and we'll start with a graph. You see that there's some stuff on other useful R code. What I want to do is I want to provide a graph here that I'm going to save now. I just retyped this part of the code, which is to ask you or to prompt you to create a scatter plot with a simple linear regression line. And what we have is we have this xy plot function. We have our outcome variable. We have our tilde, which we can think of as an equal sign in the equation framework. We have our predictor variable. We have our data at hand. But what we added was two other optional arguments, this p and this r. We don't have to really know about this, but I just want to show you what this looks like. I'm going to click run here to run that code. And look at this. What this shows you is probably some of the most useful information you can have to get an intuitive grasp of the data at hand and the outcome variable within a simple linear regression framework. This right here, this line right here, is the regression line, the simple linear fit line, superimposed on top of the scatter plot between an x variable and the y variable of interest. So as long as the x and y variable are numeric, actually even if they aren't, we can always fit a linear fit line. But you can actually see what we're trying to do, perhaps. this linear fit line is a mathematical function. And by function, we're just simply saying, what is it, whatever input of x you have, you're doing some machinery to it to get some output of a predictor variable y, or y hat. And this function is simply expressed by one mathematical equation. Maybe in some classes, you might have talked about y equals mx plus b. This is certainly my case, y equals m x plus b. If this is inscrutable to you, that's fine. But this is what we often talked about in, I think, algebra or calculus class. And in the simple linear regression framework, it's simply to say that we can talk about we can understand this line to be defined as the result of two numbers. Namely, what is the value of this line at the intercept, and what is the value of this line given its slope. And the slope is the rise over the run. It is how steep or how shallow this is. So the higher the slope is, the more steep this line is going to be. And the intercept tells us where to start this line. So if we had an intercept of, if you notice, we can already see that this numeric line right here, this linear fit line, is adequately summarized by both our intercept of negative 13.33 as well as our slope. I know it's not that clear to see, but let's see if we can increase this pane, and I'll try to see if this is a little more clear to understand. I'm going to annotate this page here, and pardon my terrible writing here, but I'm just going to extend this linear. Actually, I'm going to use some. I'm going to clear. So I'm going to extend the linear fit line beyond or below the positive values. So let me draw a straight line here. If we were to draw the straight line beyond 0, which takes us into the territory of data extrapolation, or in this case, nonsense values, we can more clearly see where the intercept value comes from. I have this mysterious red line here. This is where our intercept is. This is going to be negative. This intercept right here is going to be negative 13.33, which is equal to the intercept, or the value of y if x equals 0. We could say the predicted value of y, by the way. Okay, let me see if I can move this out of the way so we can see what's really going on. Ugh. Shoot. That's not good. There we go. Nope. Well, we'll deal with that later. Okay. The other value, the other data point we need is, of course, the slope. Slope is equal to what I've often been taught, the rise or the increase of x, sorry, the increase of y over run, or increase in y given a 1 unit increase in x. And again, we can say predicted, a predicted increase. And what this says is that this equals, in our case, this equals 1.13. And this is where a positive value also is important, because it means that given a 1 unit increase in rurality, our expected value of y will also increase by 1.13. So this is not exactly, this is a positive association, but it tells us exactly in units of y how much our outcome variable will increase. It does not tell us anything about units of x, except that with a 1 unit increase of x, whatever that value is of x, y will increase by 1.13. So again, we're talking about units of y here. And that is murder rate. In this case, it is the murder rate per 100,000 people. So what this says is given a 1 unit increase of x, again, whatever unit that may be, the y variable increases by 1.13, or 1.13, the murder rate increases 1.13 per 100,000 with every increase of x. And I talk about both the magnitude in terms of its interpretation, but also its direction. So here we can have an implied positive value, which means that the association is positive. If this slope were negative, it would mean that we'd have a negative association. We actually don't see that in these data, but a negative slope simply means that the association would be negative. So it would mean that we're kind of going downhill. And if I could just draw that, right? This is downhill, this is uphill, right? This is negative, negative, this is positive. These two distinctions are elementary, but crucial for understanding the simple linear fit line. So when we talk about intercept and slope, now we can understand it in terms of these two numbers. That this linear fit line doesn't really tell us exactly with a 100% certainty what our y variable is. Just take a look at this. For example, you can see that some data points are approximated well by the data, or by the model rather. I'm circling those. But some are not well predicted by the model. Here's one that's not well predicted. Here's one that's not as well predicted. Again, that's relative to the model. What does this tell us? Well, it tells us kind of a truism, which is that some data points are well predicted, some are not. And I just realized I circled everything now, so now you cannot tell. But let me clear all the drawing. And I just want to talk about this idea of prediction within the graphical framework. Not only can we summarize our linear fit line and understand it as a model, but given that we talk about it as a summary or as a model, it's going to be less than 100% perfect. That is, given our value of x, we may not know with 100% certainty. In fact, it is probably most likely that you won't understand with 100% certainty what your x variable is going to be. So some countries, for example, in this data set, some data points or observations are going to be well known. So given a particular value of x, we may have greater certainty in some cases than in others, but we could be somewhat off. So given what we could expect from our model might predict some countries well, like as it does with this country, because our model is predicting this y hat. All the y hats, by the way, are on the x line. The actual observed points, or y i's, are these little data points. And we talked about that in the last section. I kind of went quite into detail about what these little data points mean. And that's important because this is where the idea of variation and explain comes into really into a high gear or into focus. All we're talking about when we talk about the R squared is we're saying, what is our variance explained in our outcome? So I'm going to talk about these data points because we can explain them a little bit better, given as a function of what we can explain versus what we cannot explain. And you can see that our line is also a function of these less than accurate data points. Now, here we're not partitioning the variance into what is explained and what is not explained. Except in a way we are. We're not partitioning particular data points, but we are talking about an overall summary statistic that tells us how well or what proportion of the variance can we explain. In this case, we have an R squared of 0.61, which tells us that we can have about 61% of the variation in our y variable is explained by this linear model. And what it tells us is that 40% of the time, 40% of the data rather, are not well explained. Sorry, 40% of the variation is not well explained. Now, I would not take too much emphasis on the R squared, because I can tell you in practice we often don't emphasize it too much because R squared, while it can be predictive, it may not provide us with much understanding without knowing the context. And in most real-world situations, you probably won't even experience or encounter a very high R squared, even in this case, unless you're really trying to use some predictive algorithm that really feeds back into your data. Because we're more interested in understanding and interpreting what goes on with particular values of X. Sorry, with particular values of X and Y. But the main point is that we can still summarize the overall fit of our regression line. So let me clear all this with that R squared number. So if you wanted a summary statistic that sort of explains how well your model fits the data, you could give them an R squared of, you can tell them what the R squared is. And I can tell you, an R squared of 0.61, while it doesn't look so hot here, is actually a very good linear fit approximation. And it's pretty analogous to correlation, although it's non-directional because the R squared is always going to be positive. So the lowest R squared can be is 0, and the highest it can be is 1. And an R squared of 0 simply looks like this linear fit line in a cloud of mosquitoes, as opposed to this R squared of 1 would be, if we knew what X is, then we would know exactly what R is. It means that there is no gap between our observed data points and our predicted value of our data. So you can see that this is the Y hats, but that discrepancy is the variation unexplained by our predicted model. So I hope this clarifies both the utility of R squared, but also what its intent is overall conceptually. Let me see if I can rephrase it. When we talk about the simple linear model, we're just talking about this line right here. This model is a line and it has a mathematical equation. And when we talk about the variation explained, we're talking about how well this line fits and predicts the outcome, as opposed to how many times or how large are the distances between an observed reality and our predicted linear reality. And we can see that this observed discrepancy, the larger these discrepancies are, both as a function of the number of discrepancies as well as their distance from the line, that decreases our R squared. Are there any other questions about that? Okay, so we talked a little bit about that in terms of prediction. Now I want to clear this console and I just want to go to the math now. Now that I think we have a better understanding of this. And then finally I want to, if we can, cycle through some other data points within the environment and see if we can actually just kind of visualize what other variables might look like if we look at their linear association with murder rate. And I encourage you to play around with the data on your own as a tool to understand and interpret the regression output. So practice interpreting what these models are and what they might mean, and practice explaining them to people who are not statisticians, because this is going to be the most important task as a statistician, I think, is talk to non-experts. So talk to your friends, family, if they can deal with it. Try to see if you can tell the story in your own words. What do you think is going on? But most importantly, translate this into a human language, because this is mathematical language. And then briefly, the mathematical language is here. I typed y equals mx plus b. We can say y hat, or our predicted value, is a function of the intercept plus the slope coefficient times whatever value of x we have. And what this says then is we can understand what our linear model would predict if we know only two coefficients, which is pretty powerful. So this means that if we have, say, a rural value of 40, then it can be approximated by whatever this might be, which is like 32. All this means is that if we put into this linear model, say 40, and we multiply by 1.13 and subtract 30 or 13, then we get our estimated value. And all that means is if we have 40, we're going to get a value of, what, 32 or something, 34 maybe. And That's all that this is. And there's some other things to do here, but I think that's the main issue here. That's the main point of interest. And in fact, this is actually very useful to do, because let me show you what you can do within R. If I write out the equation here, then I can actually, I can basically assign y hat. I can basically say, assign values to these variables. So I can say intercept is I'm going to define as a variable equal to negative 13.33, and the slope I'm going to define using the assignment operator as a value of 1.13 or positive 1.13, and I'm just going to do that. Now, of course, this isn't necessarily part of the homework assignment, but I just want to show to you how you can define variables within your working environment. These are just two scalars or two numeric variables, that's two numbers that don't vary, rather. And then I'm going to write up the equation. I'm going to say, okay, here I have the equation. I'm going to define it as y hat. And I'm going to say whatever y hat is, I'm going to define it. So I'm going to use the assignment operator, although technically you can use the equal sign. I don't really like to say that, but you can. We can say y hat is equal to intercept plus slope times x of 1. I'm going to get rid of that underscore there. I'm going to do Control S. You can do the underscore there, but I just like to keep it rather simple. It'll complain that object x1 is not found, and it is totally right. So let's define what x1 could be. Let's say if we wanted x1 to be 40, then we can have y hat equal this value. Oops, I did not define x of 1. So we have x of 1 equals 40, and now we can know what y hat would equal. 31. So I actually said 32 y hat. So what I did with all of this stuff here, which you don't have to do, you can do this with a calculator. I just took this equation for the linear regression line, substituted the slope and the intercept values, and then put in a value of x that is within my data set frame to get a predicted value of what the murder rate would be if virality were equal to 40. And that's the predicted value. And you can see that for some predicted values, there's a discrepancy. So and in fact, you actually get a very precise value here that doesn't actually even exist in the data, but it is actually an approximation or our best estimate, our prediction of what our value of y would be if we could fit it by a linear model. It's our best guess at the value of y. And that's why we call it y hat. So if we redefine x1 as some other data point, let's say let's define x1 as a value of 10. So I'm going to replace the x1 here with another value. You can see that number changed. And I'm going to run this. And again, you can do this with a simple calculator. I'm just going to find out what the y hat is if x equals 10. Well, you can see that our linear model would predict already a negative number here, which is interesting because you can actually see that that would make sense, because if you look at our histogram, our scatter plot, you can see that 0 is already hovering above us at a value of 10. So we already know, we're already out extrapolating. If we even go to a virality of 10, we're already encountering some nonsensical numbers of our predicted value. So our model isn't going to be very good for predicting low rural countries. And you can see that this is the case here. You can see that it's low, but it is definitely not going to be very predictive. It will give us a nonsensical value. So sometimes y hat is going to be, our predicted values are not going to make much sense. And we need to update our model with more data, or maybe some other approximation, or with dropping outliers that don't make sense, or restricting and redefining the sample. There are many different ways you can alter the model, but the starting point is, I think, you can write out this code within R, and you can swap out different values. So let's see where we might get a value of x that would produce a y hat that is going to be more logical. It looks like around x of 15, you of course get a more positive value, but it looks like from our figure, you could probably go a little bit lower. So I'm just going to run these 2 lines of code and see what happens if we have x of 12. What's a predicted value of y? That's where you get about to 0. So what this says then is that the proportion rurality of a country is going to reach a predicted value of 0 by around a value of 12. I want to show something else to you. This might illustrate the example of slope. If we have x of 1 of equal to 20, let's do this. We get a value of 9.97. Okay, let's increase that by 1 value. How much is our y hat going to increase? Well, remember what the definition of a slope is. It is the value of increase in our y hat with every increase, 1 unit increase of our x. So if we increase the x value by 1, we're going to just add 1.13, our slope value, to this y hat right here. And let me show that to you. You're going to see this increase. So we saw an increase of something like 9.6 or something like that to just a shade above 10. So we saw an increase of about 1.13. And we can even increase this value to 2, another value. You're going to see another incremental increase by 1.13. So the next value is going to be, of y hat will be 10.4 plus 1.13, which will be 11.5. There you go. And then we can do this. If we want to do another unit increase, you'll see it increase again. This takes us to our definition of intercept, which is the value of our y variable when x equals 0. Let's run that. That'll be negative 13. You're going to see this y hat, our predicted value, be negative 13.33. So this is a good example of how to use R within your environment to use different predicted values. And you can see what I typed out here. It's not available in the code, but it's one way to look at R. And you can look at the other R tutorials to view R as a fancy calculator, as I call it. And I encourage you to look at those R tutorials. But aside from that, I also encourage you to run this nice, handy x, y plot function, but look at the other variables in the data frame. So if we look at, say, population, we can just type the word population here. We can type the variable name after that tilde, because that's the variable we're interested in, and we're interested in predicting that murder rate. Here's a good example of a model with a predicted value of y hat where the slope is negative. So we could even do the linear model stuff here, but I guarantee you'll find a negative slope. But you'll see some limitations of our simple linear model. Namely, in some cases, it's not going to be very predictive at all. Look at that variation here. So given our value of x, it's not going to be very predictive. And in fact, it's going to be, in this case, it's largely drawn by our outlier, which in this data set is the United States. It's much larger than the other countries. So of course, this outlier, this one is not like the other variables in the data set. It probably doesn't make sense to include it, or you can make other choices. You may want to model using another variable. I think last time we looked at GDP. So if we put in GDP, for example, we could look at that. It's going to not look very good either. It's also a negative association, but you'll see that it too is a function of what seems like discrepant data points. But you can still model the data as a negative association, but you have to assume that it's a linear association. You're making a big assumption, by the way, about middle-income countries here, which we don't seem to have as many in this data set. It's only a data set of, what, 8 countries? Sorry, yeah, 8 countries. But I encourage you to look at some others. Let me find another positive variable. I believe internet and, no, is internet? I think internet is positively associated. I believe we actually show that. I believe we tested on this. Is this positively associated? Oh, sorry. We want to have internet typed here. Oops. has lots of suggestions here, but these are other functions. Let's look at internet. And here are the internet variables. This is the proportion using internet. So that's actually a negative association. So rurality seems to have a positive association. Most of these seem to have a negative one. I'm not sure what else you could look at. But in any case, it's useful to look at these. And if you have time, take a look at some of these other interesting aspects. I think we could look at birth rate. Birth rate seems to be positively associated with rurality. I just know that from my own background knowledge. This is where domain or background knowledge helps. Yeah. Here's another example of positive association. This is where the slope is positive. But I encourage you to look at those figures and also see if you can try to run this code using different predictor variables. Anyway, I hope that was useful. We talked about, essentially, just to review, I know we got a little bit over. We basically talked about 3 points. One was a review of concepts. Review of simple linear regression. As a predictive model that is widely applied in data science. Then we talked about elements of the visualization of the predictive model. And this is simply what we see in the lower right-hand panel. We have the X variable and we have the Y outcome. And we talked about interpreting and using coefficients within a predictive framework. So we talked about R squared, intercept, and slope with the aim of predicting what Y would be, even if we don't have the data at hand. So we started off with a visualization. We talked about using those coefficients. Anyway, I hope this was useful. This video will be posted to the YouTube website. So if you have any questions, please feel free to interact with me or anyone else on the course website. But I hope this was useful for you, and I really much enjoy sharing this. Thanks a lot.